Let's take a look at Proposition 11 from Book 2. As you know by now, this is a brilliant construction. And what I'd like to do is I'd like to walk you through the construction first, in case you had a little bit of trouble with that, and then we'll talk some about the proof. But first, let's actually build the figure. So we begin with line AB, which we're going to draw like so. So there's line AB, and I will label it as well, line AB. And so what we have to do is we have to cut line AB in such a way that the rectangle contained by the whole and one of the segments, that is to say, the rectangle contained by AB plus one of the pieces after we cut it, is going to be equal to the square on the other segment. So if we cut it, say, here, then the length AB plus the little piece here, that rectangle, right, built out of those two sides, needs to be equal in area to the square built on the other piece. So this is quite a challenging thing to do. But Euclid's solution, of course, is brilliant. So we have AB, and the first thing we're going to do is complete the square, which by now you shouldn't have any trouble making squares. So let's go ahead and do that. I'm going to draw in a few things here, just as some guides. This is probably the kind of way you do it as well. So, and then right now what I'm doing is I'm, of course, producing my perpendicular. Right, this should all look very familiar. And then I'm simply going to drop this line to there. And of course it has to all be the same length because it's a square, so the sides all have to be the same length. So now I'm going to draw another circle there, and this gives me, of course, the length of my side. And so now I can complete that first side there. And then since I have this point, drawing this side is going to be pretty straightforward as well. I just need to imagine that this is a triangle and then copy the triangle over. I can do that by drawing another circle here. This, of course, gives me the length of this piece, and then if I draw another circle here, it'll give me the length here. And then I can join that, and there's my other point. Okay, so there is my completed, whoops. So here's my completed square, just like so. And this is how I expect that you drew it using your ruler and compass. That's the basic idea. So I'm going to hide all of these intermediate lines just to clean things up a little bit, and then we'll carry on from there. Okay, so here is our cleaned up square A, B, D, C. So the next thing we have to do is establish point E, and we do this by bisecting AC. Again, a very simple operation, one that we've done countless times. The easiest way, of course, is to simply use two circles rather than going through all of the steps, as you know by now as well, so we'll just do it like this. Right? This is probably how you've gotten used to doing it. And so now we can choose point C, and then Euclid tells us to join point E rather, E to B. I'll label that. Now, of course, your diagram is going to look a lot messier than mine here because you will still have in all of your pencil marks for the circles, but I've cleaned mine up just to make it easier to follow. So we've got E here, of course, is bisecting AC, and then what we need to do is essentially rotate this line around to here so that when we continue CA to point F, e to f is equal to e to b, which of course is as simple as drawing another circle. We draw a circle with radius EB, and that of course is going to give us our line. So I've just extended that like so, and now I can officially join it to there. And this of course is going to be for us point F. And now of course we have to draw a new square, a second square. So the square is going to have side AF, and we're just going to draw it here, and it's going to be square FH. So I'll do all those steps as well. And to make this easier on myself, I'm actually going to extend this out so I have another point to work with. Okay, so arbitrarily I'm going to make that our circle. And then I need draw one circle there, and then the other circle there, and of course now I have my perpendicular. Just going to go off in that direction, and then it just needs to be the same radius. So draw a circle there. And this now gives me that point. So I have the perpendicular line, and I know how long it is. Now I just need to drop the perpendicular down to there, which of course will be accomplished with a couple more circles. So first circle goes there, and I could theoretically just go ahead and join it now where these 2 points, this circle touches this line, but now the software knows exactly where that point is. You're not going to know if you're using a paper and pencil here, compass and ruler. That's going to be pretty much impossible to determine exactly where that circle touches that line. So instead, I'm just going to draw another circle with radius AF, and that will definitively give me that point. So that's much less ambiguous. All right, so now we have our square AFGH. And we need to continue GH down to point K, which I'll do like this. If you're using a compass, it'll be easier, because the point will be immediately apparent. All you have to do is use the ruler. Join H and K now. That's supposed to be K. The reason, if you're wondering why you tend to skip I and J as letters, it's because those are difficult to read and it's easy to confuse them for each other. I and J can be confused for each other. We just generally want to make things less ambiguous. There we go. So the clearer things are, the better. So I had to find some other thing to label I. So that it would allow me to produce a K. All right, so we've got the figure is now complete. So we have now cut line AB at point H. How did we do that? Well, we first completed the square. We bisected AC. We drew this line to B. We took this radius and used that to produce line EF. And then we chose AF, and we used that side to produce a square on top of AB, and we continued GH down to K, and this produces our cutting line. And so H then is the point which solves this problem for us. So now we have cut AB at a point such that the rectangle built on AB and BH, that is to say this rectangle here, rectangle HD or BK, whatever you want to call it, this rectangle is equal to the square built on AH. So our square there. Now it's easy to say that, but now we have to actually prove it. I'm not going to explain this proposition in quite the same detail as Euclid does, but I hope that my explanation will be sufficiently clear and you'll understand why Euclid makes the moves that he does. So to begin, let's take a look at how proposition 2.6 applies to our proof. So remember, what we're trying to prove is that this rectangle here, rectangle HD, is equal in area to rectangle FH, the square up here. And that point H is the point which makes this relationship possible. That is to say that we've cut AB at point H such that the rectangle made up of the whole, which is equal to the side BD, and the segment HB, which is this rectangle here. So the rectangle made up of the whole plus HB, this rectangle is going to be equal in area to a square built on the remaining segment, which is AH, so this square here. And to prove this, Euclid appeals to proposition 2.6. Well, what does proposition 2.6 say? You'll remember that proposition 2.6, we begin with a line segment, which in this case is going to be AC. We bisect that line segment here at point E, that's what we've done, and then we add on an additional line segment, which in this case is FA. So given those relationships, we begin with the line segment, which we bisect, and then we add on some unspecified length. It can be any length, it doesn't matter. In this case, it's simply length FA. Okay, with those relationships, the following becomes evident. And so the square built on FE, so if you can imagine a square out this way, FE, the square built on FE is equal in area to the rectangle built on CF and the remaining segment, or the segment here that we added, FA. So actually it's going to be the same size as this rectangle right here. So the square built on FE is going to be equal in area to this whole rectangle here plus the square on AE. So if you can imagine a square out there. Now I've actually drawn this out for us to make it a little bit easier to see what Euclid's talking about. And so notice, for instance, that this line segment here is identical to FG, which makes it this whole rectangle here identical to the rectangle right here. So that's important to understand. All right, so let me walk you through 2.6 again, just to make sure that we understand how it applies in this case. So the square on FE, which is this square here, is going to be equal in area to the rectangle, this rectangle here, plus the square on AE, which is this square there. Now, how do we know that this is true? Well, we know that because E bisects this line segment, that this rectangle here is going to be equal in area to this rectangle. So these two rectangles are equal. However, this is also a square. Here we have a diameter, and we have a complement on this side of the diameter, which means that this is also going to be equal. So the three rectangles that I've marked with X's are all equal to each other, right? So this one is going to be equal to this one right there, which means if we add the remaining circle here, that this rectangle is equal to the gnomon right there. I hope that you can see how that's true. So this whole rectangle is equal to these three rectangles here, or these two rectangles plus the square. And that only gives us one space remaining, which is the square on AE. So what we find then is because these three rectangles there are equal to these three, once we add the remaining square here, we've completed our square on FE. So what we find then is, yes, the rectangle built on FC plus and the segment FA, so this whole rectangle here, plus the square on AE is in fact equal to the entire square on FE. So that's proposition 2.6. Now Euclid appeals to proposition 147, our Pythagorean theorem, and he does so like this. He says, all right, so the square on FE is equal to this right here, and we know that that's equal to the rectangle, which is the same as this rectangle, by the way, plus the square on AE. Well, as it turns out, FE is also equal to BE. this line there, because remember we drew them to be equal lengths. So we can even imagine the square on FE, we can even imagine it being drawn out something like this, right? Okay, so by the Pythagorean theorem, then we have a square over here, which, by the way, remember this is our square, which I'll just draw it like this, but just remember that it's this. These are the same, right? Those are the same. So we have square on AE, which is this one, is going to be equal to this square on BE once we add the square from AB to it. So the square on AB, we could draw it up right like so, but we actually have it already drawn in here, right? It's simply the square on AB that we've been looking at this whole time. So we know then that the square on AB, right here, plus the square on AE, which is this one or this one, is going to be equal to the whole square on BE. But it's also true, right, that the square on BE is equal to the square on FA. So here's what we've determined so far. Because the square on BE is equal to the square on FE, then once we add AE, the square on AE, and then to each, we're left with two different things, right? We're left with this rectangle here on this side and this square on this side, and these are actually equal. These are equal. Let me walk through that again. So remember, FE is this square here, right, which is the same as the square on BE. And the square on BE is equal to the square on AE, this square here, plus the square on AB, which is our entire square here. But it just so happens that the square on FE is also equal to the square on EB, and it is equal to the square on AE plus the rectangle here. So what we can do then is we can delete or imagine removing the square on AE from both sides, right? Because this plus this is equal to the square on FE rather. And likewise, the square on EB, which is equal to the square on FE, is equal to the square on AE plus the square on AB. So if we just get rid of the common square, which is the square on AE, what we find is this rectangle here is equal to the square on AB. Okay, so far so good. Now don't forget that the square that I've drawn on this side really is the same as the square inside the rectangle inside the figure, right? The rectangle out here is the same as the rectangle right there. And so we notice that we have some common areas. For instance, this area is the same as this area here, right? And this area also appears within our square. So if we delete that area, so if we remove this common area, right, so if we imagine getting rid of this here and we remove it, we're left with two areas. So I'm removing it from this rectangle here and I'm removing it from our square, right? Because this is equal. So equals subtracted from equals are equal. So that leaves us with two areas. So we're left with this green area up here and we're left with this little rectangle down here. So we know that because this whole rectangle is equal to the square, when we subtract the equal quantities of this rectangle and this rectangle, the green areas are going to have to be equal, right? And of course, we know that this square is really equal to this square. And what we have proven then is that this area must necessarily be equal to this area there. So we really have accomplished what we set out to accomplish. Point H cuts AB in such a way that the rectangle built out of AB and BH, which is this rectangle there, is equal in area to the square built on the remaining segment, which is the square built on AH. So I hope that that has helped if you found this one a little bit tricky. If you haven't already gotten into a habit of mapping out some of these more complex propositions onto the figures which apply them, you may want to start doing that because it does make them easier to see and easier to understand. Right? If you try to do it all in your head, it's very, very difficult to understand how on earth proposition 2.6 applies in this case. But once we draw it out and follow some of the steps and follow the reasoning through, it does become a little bit more apparent.